Initially, there was an infinitely dense mass of matter. This mass underwent an explosion that gave rise to the formation of atoms, molecules, stars, and galaxies that we can observe today. For decades, this has been the explanation offered by physicists. However, recent research has introduced a new perspective that suggests the universe does not have as early an origin as initially believed. Instead, it may be part of a cyclical process in which the universe goes through a series of cycles of expansion and contraction, possibly in an infinite loop. Brian Cox, a renowned physicist, has also raised doubts about the Big Bang theory, arguing that something cannot arise out of nothing. This questioning adds an intriguing element to the discussion. In addition, research from the James Webb Telescope has revealed information that contradicts the idea that the Big Bang marked the absolute beginning of the universe. This leads to the fundamental question: if the Big Bang was not the beginning of the cosmos, then what was? Join us on this journey to the beginnings of the cosmos, where we will explore the frontiers of the Big Bang and answer this question and many more. If you are interested in keeping up to date with news about the universe and its surroundings, subscribe to our channel, hit the like button, share this video to reach more people, and turn on the notification bell. Scientists have developed a detailed understanding of the universe in its earliest stages, known as the Big Bang theory. According to this model, the universe was much smaller, hotter, and denser than it is today. Approximately 13.8 billion years ago, during that period, all the elements that make up our world were formed in a matter of minutes. In this theory, our universe, including stars and galaxies, was once as tiny as a peach and had an extremely high temperature of over a quadrillion degrees. Interestingly, this astonishing narrative aligns consistently with all current observations. Astronomers have investigated everything from the remnant electromagnetic radiation of the early universe to the abundance of the lightest elements and have found that everything agrees with the predictions of the Big Bang to the best of our knowledge. This description fits the reality of our universe perfectly. However, despite its apparent robustness, we know that the Big Bang theory is not the complete picture. There's a missing piece to this puzzle, and that piece is an understanding of the first moments of the universe. This challenge is due in large part to the limitations of the physical theories we currently employ. The combination of general relativity and high-energy particle physics provides us with a valuable conceptual framework. However, as we delve deeper into the initial moments of the cosmos, the mathematical complexity increases significantly, reaching a point at which our current methods cannot provide meaningful solutions. One indication of this difficulty is the existence of a singularity, a point of infinite density at the beginning of the Big Bang. This notion suggests literally that the universe was once compressed into an infinitely small and dense state, which seems absurd. To address this challenge, we need to explore new frontiers in physics, develop an approach that overcomes these limitations, and provides a more complete understanding of the first instance of the universe. Our current instruments and theoretical frameworks are not robust enough to address this challenge. So we need to develop new physics that can encompass and explain gravity and the other fundamental forces at extreme high energies. This is precisely where string theory comes into the picture. This theory aspires to be a physical model capable of unifying gravity with the other fundamental forces, especially at ultra-high energies. In essence, string theory posits that it can provide an explanation for the first moments of the universe. Within string theory arises the concept of an aeon, which takes its name from the Greek word meaning configuration or age. This idea suggests that the Big Bang, as we know it, was the result of an earlier event, implying that it was not the absolute beginning but rather a part of an ongoing process. Extending the notion of an aeonic universe has led to the development of a related theory called cyclic cosmology. Although the idea of a cyclic universe has been considered for millennia, string theory provides a solid mathematical basis for this conception. In the framework of cyclic cosmology, the universe functions as if it perpetually oscillates between large explosions and collapses in an endless cycle that extends infinitely into the past and future. This theory of cyclic cosmology was proposed by the eminent physicist Roger Penrose, who was awarded the Nobel Prize. Penrose was intrigued by a remarkable mathematical relationship between the early universe, characterized by extreme density, heat, and smallness during the Big Bang, and the future state of the universe, which is characterized as extremely cold, expanded, and devoid of matter. The theory suggests that these two states become mathematically identical when pushed to extreme limits. Although it may seem paradoxical, the total absence of matter could be the driving force behind the creation of all the matter we observe in the universe. From this perspective, the Big Bang originates from what remains almost imperceptibly after all the matter in the universe has been consumed by black holes that eventually evaporate into scattered photons in a vast void. The universe emerges from what, from another point of view, essentially approaches nothingness, although this nothingness is still a form of something that constitutes a physical universe, albeit an empty one. The mystery lies in how the same state can be interpreted as both a cold, empty universe and a dense universe, depending on the point of view. The key to this understanding lies in a complex mathematical technique called the conformal transformation, which is a geometric transformation that changes the size of an object while retaining its shape. Roger Penrose showed that the cold, empty state and the hot, dense state can be connected through the scale transformation, aligning their spatiotemporal structures despite their differences in size. However, Penrose argues that the concept of time loses its relevance under these extreme physical conditions. In cyclic cosmology, the sequence of events unfolds from an old cold state to a young hot state. The presence of the hot and dense state is the result of the previous cold and empty state. However, this causal relationship does not follow the usual pattern in terms of time, since in these extreme states both size and time lose their conventional meanings. The cold empty state and the hot dense state exist on separate timelines, which means that from the perspective of an observer within its own time frame, the cold empty state would continue indefinitely. Physics and philosophy are intertwined in this realm of cyclic cosmology. It provides speculative and detailed explanations for the origin of these cycles. However, even if Penrose's ideas gain support in cosmological advances, a deeper philosophical question still lingers about the origin of physical reality itself. How did these cycles come into existence?
This leads us to ponder the reason for the existence of something rather than nothing, which is one of the fundamental metaphysical questions. For our purposes of discussion, we will focus on explanations within the realm of physics. There are three possibilities to consider in exploring the origins of these cycles. First, there may be no physical explanation at all. Second, there could be an infinite series of cycles where each cycle represents a different universe, and the initial quantum state of each universe is somehow determined by some aspect of the universe that preceded it. Finally, there is the option of a single cycle in a repeating universe, where the beginning of the cycle is explained by some feature of its own end. These possibilities are attractive because they avoid the need for uncaused events and provide a more complex explanation within the physical framework. In the realm of physics, Penrose proposes the idea of an endless sequence of cycles influenced by his interpretation of quantum mechanics. In quantum mechanics, a physical system exists in multiple states simultaneously until it is observed, at which point it randomly collapses into a single state. Penrose suggests that each cycle is influenced by random quantum events that give rise to variations between cycles. This concept opens up promising possibilities for experimental physicists, as it suggests the possibility of detecting subtle traces or anomalies in the remnant radiation of the Big Bang. The quest to understand the origins and nature of the universe has been a fundamental pursuit of human curiosity and scientific inquiry for centuries. From ancient philosophical speculations to modern cosmological theories, humanity has continually sought to unravel the mysteries of existence itself. In the context of contemporary astrophysics and cosmology, the exploration of cosmic origins has led to profound discoveries and intriguing theoretical frameworks that challenge our fundamental understanding of time, space, and matter. One of the enduring questions that have captivated physicists and cosmologists alike is the nature of the universe before the Big Bang. While the Big Bang theory has provided a compelling explanation for the evolution of the universe from a hot, dense state to its current expansive form, it leaves open the question of what preceded this cosmic event, if anything. The concept of a pre-Big Bang era raises profound philosophical and scientific implications, pushing the boundaries of our knowledge and understanding. Several theoretical paradigms have been proposed to address this question, each offering unique insights and perspectives on the early universe. One such concept is that of the multiverse, which posits the existence of a vast ensemble of universes, each with its own distinct physical properties and fundamental constants. In the multiverse framework, our universe is just one among many, each emerging from different initial conditions and governed by its own set of physical laws. The idea of a multiverse arises naturally from certain interpretations of quantum mechanics and cosmological inflation theory. According to inflationary cosmology, the rapid exponential expansion of spacetime in the early universe could have led to the formation of pocket universes within a larger multiversal landscape. Each pocket universe would have its own unique properties, shaped by random quantum fluctuations during the inflationary epoch. While the multiverse hypothesis remains speculative and difficult to test empirically, it offers a compelling solution to the fine-tuning problem in cosmology, the apparent improbability that the fundamental constants of nature are finely tuned to allow for the existence of complex structures such as galaxies, stars, and life itself. Another intriguing possibility is the notion of a cyclic or oscillating universe, which suggests that the universe undergoes a perpetual cycle of birth, evolution, and demise. This idea, rooted in ancient cosmological traditions, has gained renewed attention in modern theoretical physics. In this framework, the universe goes through a series of expansions and contractions, with each cycle leading to a new phase of cosmic evolution. The cyclic model proposes that the Big Bang was not the absolute beginning but rather a transition point in an ongoing process of cosmic rebirth. This concept aligns with certain versions of string theory, which suggest that the universe's evolution is driven by higher-dimensional processes and interactions. As our understanding of the universe continues to evolve, it is clear that the quest to uncover the true nature of cosmic origins will require a combination of theoretical innovation, observational breakthroughs, and philosophical reflection. The search for answers to questions about the pre-Big Bang era and the ultimate fate of the universe remains one of the most profound and exciting challenges in contemporary science. As we push the boundaries of knowledge and explore new frontiers, we inch closer to unraveling the mysteries of existence itself and gaining a deeper appreciation of our place in the cosmos. In addition to the concepts previously discussed, another fascinating avenue of exploration in the quest for understanding the universe's origins involves examining the implications of quantum gravity. Quantum gravity aims to unify general relativity, which describes the force of gravity on a cosmic scale, with quantum mechanics, which governs the behavior of particles on the smallest scales. One of the most promising approaches to quantum gravity is loop quantum gravity, LQG. Unlike string theory, which posits that fundamental entities are one-dimensional strings, LQG proposes that space-time itself is quantized. This means that space and time are composed of discrete, indivisible units or quanta, rather than being continuous. According to LQG, the fabric of spacetime is woven from these fundamental units, which could profoundly alter our understanding of the universe's early moments. Loop quantum gravity also introduces the concept of a Big Bounce as an alternative to the Big Bang. In this model, instead of a singularity from which the universe emerged, there was a previous contracting phase that collapsed to a point and then expanded again. This Big Bounce could provide a more elegant explanation for the universe's origins by eliminating the need for a singularity, which is mathematically problematic and physically enigmatic. This idea aligns with some interpretations of cyclic cosmology, but offers a more concrete framework by integrating quantum principles with general relativity. Another intriguing area of research is the concept of primordial black holes, PBHs. These are hypothetical black holes that could have formed in the early universe due to density fluctuations. If such black holes exist, they might provide clues about the universe's earliest moments and could even contribute to our understanding of dark matter. PPHs could potentially be detected through their interactions with surrounding matter or their effects on cosmic microwave background radiation. If found, they could offer a window into the universe's infancy and the conditions that prevailed before the Big Bang. Furthermore, the study of dark energy and dark matter continues to play a critical role in cosmology. Dark energy is the mysterious force driving the accelerated expansion of the universe, while dark matter is an invisible substance that exerts gravitational effects on visible matter.
The interplay between dark energy and dark matter could shed light on the universe's fate and its evolution over time. The precise nature of these components remains one of the most significant challenges in modern physics. Advances in understanding dark energy and dark matter may also provide indirect insights into the pre-Big Bang era or the conditions that preceded the observable universe. Additionally, advancements in observational technology, such as the development of more sensitive and precise telescopes, continue to push the boundaries of our knowledge. The upcoming observations from next-generation space telescopes and ground-based observatories could provide crucial data that either supports or challenges current theories about the universe's origins. For instance, detecting signals from the cosmic microwave background with greater accuracy might reveal new information about the early universe's conditions, further informing our understanding of the Big Bang and its antecedents. On a more philosophical note, the study of the universe's origins intersects with questions about the nature of existence and the role of human perception in understanding reality. The exploration of these profound questions involves not only empirical research but also philosophical inquiry into the nature of time, space, and causality. Theoretical physicists and philosophers alike grapple with questions about whether our current models and theories are merely approximations of a deeper reality or if they represent the ultimate truth about the cosmos. As our theoretical models evolve and our observational capabilities improve, we may come closer to answering some of the most profound questions about the universe's origins. The interplay between theory and observation, combined with philosophical reflection, will likely continue to shape our understanding of the cosmos and our place within it. The pursuit of knowledge about the universe's beginnings is not only a scientific endeavor, but also a quest for meaning and understanding that transcends disciplinary boundaries.